As shown below, light from a vacuum is incident on a shard of Chautonium, a newly discovered compound. The backside of the shard is up against an unknown material. When the light strikes the backside of the shard, total internal reflection occurs. The light then emerges from the side of the shard and resumes traveling through a vacuum. The index of refraction of Chautonium is 3.2. Determine the speed of light in Chautonium, theta, and the upper bound of the index of refraction for the unknown material. That's what this in unknown is. It's the index of refraction for the unknown material. Now, I want to go through this problem. I'm not going to solve it fully, but I want to talk about how to solve it, what the approach is. And I'm going to focus on these two bottom parts here, determining the upper bound of the unknown index of refraction and theta, which is way over here. So, to begin with, let me switch to this diagram. To begin with, you're going to need to find this angle here. And the reason why you need to find this angle is you're going to want to use Snell's law. Okay. Snell's law says in a sine, this is the general formula. It's also known as the law of refraction. You're going to want to use this because that's what's going on here. We have refraction going on. The light comes in here and then it's going from one medium, in this case a vacuum, to another one, the shard. And so that's exactly what this formula is for. It's for refraction. But these angles are measured relative to the normal. The normal is the line that is perpendicular to the surface. So this is the angle you need to measure right here. You need to figure this angle out. You know this one. Like in my case, it's 52.37. So I'm confident you'll all be able to figure out what this angle is. And once you know that, we're dealing with a vacuum. Okay? The index of refraction for a vacuum, that's well known, n equals 1. So you'll know the index of refraction, you know the angle, you know the index of refraction for the shard, so you can figure out this angle right here, this one. Okay. So let's just label these. So you need to determine theta 1, and then from that you can use the law of refraction to figure out theta 2. Okay, next up you need to figure out this angle here. This is the next angle that you need to figure out. Okay, well the problem is, and even though I've blown this up, it's getting a little crowded in here. The problem is you don't have a direct relationship between just these two, but we do have a triangle here. And remember that the sum of the angles in a triangle is 180 degrees. Okay. So you'll know theta 2, so you just need to figure out this angle right here. Okay, let me make that a little clearer. The angle I'm talking about, you need to find this angle here. Okay. I'm going to leave that up to you to figure out how to do this, but it's just geometry. Okay, just the geometry of angles anyway. You just need to go through and figure that out. Okay. Let me relabel our angle here though. Once you go through and figure out this angle, theta 3, great. Now you can use the law of refraction to figure out this angle, the law of refraction, the law of reflection. You can use the law of reflection to figure out theta 4. Once you've got that one, you should be able to determine this one. Okay. And of course, you're going to need to know this angle as well. Again, I'll leave it up to you to figure out how to get this angle. But then once you know this one, guess what? It's easy to get this one. And then it's just the law of refraction. And this time I actually mean the law of refraction. So you got to use the law of refraction here, the law of reflection here, and then the law of refraction again over here. So that's what you're going to have to do to figure out theta. Now, in unknown, what you're really determining, let me back up to here, is it's the upper bound of in unknown. And so the way you're going to do that is you are going to use total internal reflection. So our formula for that is, this is the general formula. Now this formula allows us to find the critical angle. What is the critical angle? Well, if the light comes in at the critical angle, then instead of reflecting or refracting, it will travel right along the interface. So we clearly do not have the light coming in at the critical angle here because we're getting total internal reflection. In fact, the angle must be greater than the critical angle. But we will treat this situation as if the light were coming in at the critical angle, and that will allow us to determine the upper bound for in sub b, the greatest value for the index of refraction that this unknown material could have. Now, the critical angle itself, however, is not theta sub 3, because just like here in Snell's law, or the law of refraction, the angles must be measured relative to the normal. So what we've got to do is draw the normal here. There's the normal, okay? And then this angle right here, which of course is going to be 90 minus theta sub 3, okay? That is the critical angle, or that's what we're going to treat as the critical angle. Again, it's not the critical angle. We know that because we're getting reflection, total internal reflection, but we're going to treat it as the critical angle so we can find the upper bound for in sub b, for the index of refraction for the unknown material. And that's what there is for this problem. I know I've left a few bits and pieces here for you to figure out on your own. That's because it's important for you to go through the process. But certainly if you have any questions, just reach out to me.